ठीक है सर, आप स्टार्ट कर लीजिए।
या सर,
तीन
मैं
तीन
बस
बच्चे हैं
प्रेजेंट कर
अपने
रहा
पास।
हूँ। आई हैव
ओके।
जस्ट स्टार्टेड द रिकॉर्डिंग, नाउ आई एम प्रेजेंटिंग हियर। I hope my screen is visible to all. Okay. So today's topic is D and F block elements. Okay. So the students who have the periodic table with you can please take out the periodic table, keep it in front of you, and also take out your textbook. This chapter, D and F block elements, Unit 8. Periodic table will be very much helpful for you. So a textbook and a periodic table. I'm giving you 1 minute. Please do that right now because that is very important for us to understand this topic in a good way. So in this chapter, D and F block elements, first we will cover D block elements. Okay. So what are D block elements? I will define that. I'm giving you 1 minute to please take out your textbook and periodic table. So as you can see in your periodic table, okay, so D block of the periodic table contains the elements of the groups 3 to 12 in which d orbitals are progressively filled in each of the four long periods. Okay, so basically in your periodic table you can see groups as well as periods, right? क्या हुआ? चलेगा व्हाट्सएप कर दो, व्हाट्सएप कर दिया करो यार. So basically, what are d block elements? D block elements are defined as the elements where last electron is filled in d orbital. Okay, so once you are filling as per the Aufbau principle, I hope you are all aware what is the Aufbau principle. It's the principle how you fill the electrons in a particular element. Okay, so the elements whose last electron, while filling the last electron, enters the d orbital, or more specifically, the n minus 1 d orbital, or n minus 1 can be also called as penultimate shell. Okay, so d block elements are those elements whose last electron enters the n minus 1 d orbital, or you can say the penultimate shell, which is the last shell. It's known as the valence shell, and one shell previous to the valence shell is your penultimate shell. Okay, I hope this is clear to you. And in case of d block elements, you can see there are three series mainly. One is the 3D series, scandium to zinc, one is 4D series, and one is 5D series. Okay, so you can see in your periodic table the fourth period, the fifth period, and the sixth period are basically the D block elements, and your group should be 3 to 12. The period should be 4 to 6, and the group should be 3 to 12. So all those elements that are there in the periodic table are your D block elements. Okay, I hope you would have taken out the periodic table and have seen the elements which are there in the D block. Further, if you talk about F block elements, the two series of the inner transition metals 4F and 5F are known as lanthanoids and actinoids. You can see in the periodic table the elements which are just at the bottom, the last two periods you can see just at the bottom of your periodic table are your F block elements. But we will discuss them in detail in the next topic over here, which is F block element. Right now we will focus more on D block elements. Further going to the next page, electronic configuration of d block elements. So as I said, the last electron enters the n minus 1 d orbital. Okay, so this is the general electronic configuration. Whichever I'm highlighting over here, that you also need to highlight in your textbook, because these things are very important for you. Okay, so highlight this thing. The electronic configuration of these elements is n minus 1 d 1 to 10, ns 1 to 2. See, d orbital, how many electrons can be accommodated in d orbital? 10
10,
electrons, right? And in s orbital, maximum 2
2.
electrons, right? So in that way, you can see n minus 1 d 1 to 10 and ns 1 to 2. All right. So here also you can see n minus 1 stands for inner d orbitals, which can accommodate 1 to 2 electrons, and outermost ns orbital may have 1 or 2 electrons. All right. Now I would also like to define you one more thing, which is transition elements. What are transition elements? Okay, what is the meaning of transition? Those d block elements are also known as transition elements. If I say this thing, what do you mean by transition? Because those elements are basically the transition from S block to P block. As you can see in your periodic table, on the left hand side you can see S block elements, that is group 1 and group 2, and on the right hand side you can see P block elements, right? So as you go from S block to P block, there is a transition which is taking place, and whatever is there in the center of the periodic table are your D block elements. Hence, these elements are known as transition elements. Okay, understood. Now there is one more definition of transition elements which you need to remember. Only elements of D block having incompletely filled d orbital are transition elements. Okay, so we will understand this further. What is the meaning of this? So mainly the d block elements that have incompletely filled d orbital. The d orbital should not be completely filled. What is the meaning of completely filled d orbital? In d orbital, maximum electrons that can accommodate is 10. So in n minus 1d there shouldn't be 10 electrons. If it has 10 electrons, it will be completely filled, and those elements that have completely filled d orbitals are not transition elements, but they are d block elements. Okay, understood the difference between transition and d block? All d block elements are not transition elements. You need to make sure this thing. Okay, so I will make you understand this with some examples as well. Like you can see over here, first series. See, 3D series is known as first series of d block elements. 3D series. Okay, so if it is a 3D series, the electrons accommodate in 3D orbital, and if it is 4D series, the electrons accommodate in 4D orbital, and if it is 5D series, the electrons accommodate in 5D orbital, and this is n minus 1d orbital. So ns orbital would be 6s in this case, 5s in this case, and 4s over here, if you can see in the screen. Okay, and what does the period number suggest you? If the period number is 4, if the period number is 4, it shows that the valence electron, I mean the valence shell is 4. Okay, so n minus 1 would be 3d. If valence shell is 4, the valence shell, the penultimate shell should be 3. Okay, so that way also you need to remember the name also, scandium, titanium, vanadium. I will make you remember this thing using some particular, you can say some method is there to remember these things. Okay, so here you go. The electronic configuration of zinc, cadmium, and mercury are represented by n-1 d10 ns2. So if in d orbital there are 10 electrons, okay, so I should say that the orbitals in these elements are completely filled in the ground state as well as in their common oxidation state. Therefore, they are not regarded as transition elements. So you understood the difference between d block and transition elements? Okay, so what differentiates both of them is, in case of transition elements, there should not be there should be incompletely filled d orbital, or you can say there should not be completely filled d orbital. Okay, so all the elements other than zinc, cadmium, and mercury are transition elements. Further going to I want you to underline this in your textbook. Whatever I am highlighting here is very important. You need to remember it and underline it, please, in your textbook. Let's do this example 8.1. On what ground can you say that scandium Z equal to 21? This is the atomic number, is a transition element, but zinc is equal to 30 is not. Okay, so you can read the answer. On the basis of incompletely filled 3D orbital in case of scandium, in its ground state, it is regarded as a transition element, as I told you. But in the case of zinc, which is a which has a completely filled d orbital 3d10 in its ground state as well as in its oxidation state. Okay, tell me what is the oxidation state of zinc, if you all know. Which oxidation state does zinc has? Zinc plus 2.
Plus
Okay,
2.
so if I tell plus 2, so the two electrons will be lost from the 4s orbital, because what is the electron configuration of zinc? 3d10 4s2. So in ground state, it's 3d10 4s2, and in oxidized state, it has 3d10. So in both the states, you can see there are completely filled d orbitals. Hence, it is not regarded as transition element. Okay, let's go further. Let's talk about the physical properties of transition elements. What are the properties of transition elements? See, these are all metals. These are all metals. Okay, so they should possess metallic properties. And what are the metallic properties? You might have learned this in your lower classes as well. It has high tensile strength, ductility, malleability, high thermal and electrical conductivity, and metallic luster. Okay, but zinc, cadmium, mercury, all these are not transition metals, so they don't show this property. Okay, transition metals, zinc, cadmium, mercury, they are not transition metals, so they shouldn't show this property. All right, so further let's see what are the lattice structure of transition metals over here. Okay, so first thing, scandium, titanium, vanadium, I've written all the 3D series, 4D series, and 5D series over here. Now I will cancel out zinc, cadmium, and mercury. No need to be confused if HCP is written over here, you just cancel it out. Zinc, cadmium, and mercury. Why did I cancel it out? Because they are not transition metals. Okay, let's focus on how to learn this table. Okay, so here you can see, first what you have to do, you have to write this 3D series, 4D series, and 5D series as it is. Now I will tell you the way how to remember this. Okay, so in scandium you have to see, in scandium it's HCP, HCP, and HCP. In the first group, it's HCP over here, which is hexagonal close packed. The full form you can see over here. Even in the second, it's HCP. Okay, no need to be confused over BCC is written over here or CCP. Okay, you just focus on what I am saying over here. What is important is what I have highlighted for you. Okay, I have crossed these three. I have in scandium, here I have written HCP. Here also I have written HCP, means first two groups are your HCP. Okay, let's focus on next two. Next two are your BCC, which is body centered cubic. Okay, so the first two are HCP, the second two are your BCC. Now there is one more exception which is mentioned over here, which is manganese. So manganese is an exception, so I will mark this as cross. Okay, and which is another exception, iron. You need to remember this. Iron is BCC. This you need to remember. And what are the next two? HCP. Here you will have an exception over here. Manganese doesn't have a lattice structure, so I will cancel it out. And iron, it will be a BCC. So let's conclude. Let's see from first once again. First two are HCP, second two are BCC, the next two should be HCP other than iron. And manganese is of course cross because it is not a transition metal. Now let's focus on other three. All the other three are your CCP. Okay. See this chapter, you should learn the tricks how to remember this whole table, how to learn the electronic configuration. This is how you will be able to solve the questions in the board exams. Okay. Don't mug up as it is. You should know the tricks how to learn. So what is the trick over here to remember? First, you need to write all the 3D series, 4D series, and 5D series. I will make you learn this thing also. How to write scandium, titanium, vanadium. There is a, you can see a trick how to write this down. Scandium, titanium from this 3D series, 4D series, and 5D series. After you write this down, the first two are your HCP, the second two are your BCC, the next two are your HCP, other than iron, which is an exception, BCC, then all the other three are your CCP, and the last one is cross. Why? Because they are not transition metals. Hence, they don't show the lattice structure property of transition metals. Okay, I hope it is clear to all. Further moving on, let's come to the melting point and boiling point. Here is the electronic configuration, ionization enthalpy, oxidation state. Yeah. Here only it's a melting point and boiling point is mentioned, which is very high. Okay. And why it is high? Okay. What is the bond between these metals, this lattice structure? You know what is the lattice structure over here? Let's say copper metal. Let's say there is a copper metal. Okay, so what will happen? The valence shell of the electron will break the bond due to some energy which is provided to the metal. The bond will break, and the last electron will be surrounding the atom. Okay, so what is the lattice structure over here? Metal plus with electrons surrounding the cation, and this hole is known as electron C pull. Okay, so what I wanted to say is between two metal ions, there is a metallic bond, and also there is one more bond which is covalent bond. And where does this covalent bond come from? The unpaired electrons. It comes from the unpaired electrons. A metal can also bond using covalent bond. And that covalent bond comes from where? Unpaired electrons. So you need to make sure why the melting point and boiling point of this d block elements are high, or you can say transition metals is high due to unpaired electrons. It's written also over here. The high melting points of these metals are attributed to the involvement of greater number of electrons from n-1d in addition to ns electrons. So you need to underline till here. Make sure you remember this. Okay, I will give you one example as well. The melting point of metal rise to a maximum at D5 except for anonymous of magnesium and fall regularly as the atomic number increases. Further moving on, I will tell you how the melting point of few metals is very high. Let's take an example of chromium, Cr. Chromium. Here is chromium. Here is the electronic configuration of chromium. But it is 3d5 4s1. Okay. Now tell me how many unpaired electrons are there in this chromium? If you see in case of d orbital, all 5 electrons are unpaired, and also in 4s1 means in s orbital there is one more unpaired electron. So in total there are 6 unpaired electrons. Hence in case of chromium the melting point is very high, even the boiling point is very high. Why? Because more the unpaired electrons, stronger the covalent bond. If the covalent bond is stronger, it will take more energy or more temperature to break that bond and to convert from solid to liquid or to convert from liquid to gas. So that way, more than paid electrons, you just need to remember one thing: more than paid electrons, higher the melting and the boiling point. Okay, you can write this line over there in the textbook. If number of unpaid electrons are more, melting point and boiling point is also higher. Now let's talk about one more example over here, which is it would be below over here. We initially took the example of chromium, which is 4s1 3d5. Now I'm taking the example of molybdenum. Okay, so what is the configuration? 4d5 5s1. So again, highest number of unpaired electrons. So this element molybdenum also has a high melting and boiling point. And one more example I want to give you is this one, tungsten. Okay, what is the configuration? 5d4 6s2. So you can write it over there in your textbook. The elements chromium Cr, the element molybdenum Mo, and the element W. These elements have highest melting and boiling point. So an MCQ can be asked in your exam, in your board exam, that which elements of D block have high melting and boiling point. So you just have to write chromium, molybdenum, and W. And if they ask the reason, tell due to high number of unpaired electrons. Okay. Now let's focus on the elements which have low melting and boiling point. Okay. Here is zinc. 3d10 4s2. So you can see over here there is no unpaired electron, hence no covalent bond, hence low melting and boiling point. So zinc is one example. Another example, but obvious is cadmium. Again, same, completely filled d orbital and s orbital as well, and mercury. Okay. Further moving, we will learn about the enthalpy of atomization. Atomization. It may be mentioned over here somewhere. Here you go. You need to keep in mind the enthalpy of atomization is same as that of your this melting and boiling point. So same procedure, or you can say same concept is there for this enthalpy of atomization, because enthalpy means what? The energy required to break the bonds of a metallic lattice to form a single metal. What is enthalpy of atomization? The energy which is required to break the lattice of the metal into a single atom. So that energy which is required is required to break the bond between two metals. So more the covalent bond, more energy will be required. Hence, you can say that the enthalpy would be more. So same, whatever the trend is there for melting and boiling point is the same for this enthalpy. So underline whatever I have underlined over here. Same thing. Okay, only this much things are very much important for you. The other things which I have not made you underline are not much important. They are rarely asked in the exam. Let's move further and come to the atomic size, atomic and ionic size of transition metals. So you need to start reading from here. There is an increase from the first to the second series of the elements, but the radii of third series are virtually the same as that of corresponding members of second series. Okay, so underline this part. This is important. Now here you can see in this page all the elements are written 3D series, 4D series and 5D series. Okay, so here we will only talk about the 3D series because mainly the question is asked from the 3D series regarding the atomic size, whose size is more, whose size is less. Okay, so in this case remember scandium is more than titanium, greater than vanadium, greater than chromium. Chromium is greater than this manganese, iron. Okay, and here iron here do equal to, here also do equal to, and in case of copper, copper will be greater than nickel, and zinc will be greater than copper. Okay, so I'm writing. Open this page. Start writing. Here also, here only mention scandium is greater than titanium. So make a greater than sign towards scandium. Make a greater than sign towards scandium. Again here also make a greater than sign. Same here. Chromium also. Manganese also. Now come to iron. Here do equal to sign. Means I mean to say that in case of iron, cobalt and nickel, the atomic size is nearly same. So equal to here, equal to over here. And in this case, it's opposite. The size of copper is higher than nickel. So make a greater than sign towards copper and towards zinc. And what is the reason for this? See, in this case, still iron, the Z effective dominates as compared to the screening effect. I hope these two terms you might have understood in that chapter, periodic properties. Okay, so from scandium to iron, the Z effective dominates over screening effect. Hence, as you go from left to right, your size decreases. From scandium to iron, the size will decrease, and further from iron to cobalt, the Z effective and screening effect is nearly equal. So here it will be equal to sign, and as you go here, nickel, copper, and zinc, the screening effect dominates over Z effective. Hence, if the screening effect dominates, the size of zinc would be greater than copper and size of copper would be greater than nickel. Now talking about as you go from up to bottom, top to bottom, what will happen? As you go from top to bottom, let's say from 3D to 4D. Now you might be knowing this thing. As you go from top to bottom, the size increases. So the size of all the 4D series would be higher than the size of 3D series. And similarly, the size of 5D series should be more than 4D, but it is not like that. The size of 5D series is equal to the 4D series. Why? Due to lengthenide contraction. And what is this lengthenide contraction? Have you learned this? These are lanthanoids, and due to poor shielding effect of 4f electrons, the size will decrease. Hence, their size will be nearly equal to the 4D series. So, what is the trend? The size of 4D is greater than the size of 3D series, and size of 5D series is equal to the size of 4D series. So, whatever I am saying, please write it down as well. These questions are very important, they are asked. When we talk about the atomic size and the ionic size here. Now let's talk about ionization enthalpy. What is the meaning of ionization enthalpy? The energy required to remove an electron from the valence shell of the element is your ionization enthalpy. Right? So first, let's write it down. All the elements: scandium, titanium, vanadium, chromium, manganese. Like from scandium to zinc, we are writing this down, and we are also writing the atomic number over here till 30. Okay, now let's first understand the electronic configuration. This part I'm making you understand this table 8.2 on page number 214. Okay, so first I'm writing the elements, the 3D series elements, then I'm writing the atomic number from 21 to 30. Now I'm making you learn how to understand this electronic configuration. See, if it is 21, So it will be 3d1 4s2, right? So 1 is over here and 2 is over here on the top. 21. So what is the reverse? 12. So you need to remember how to learn this. The reverse of 21 is 12. So 1 will come over here, 2 will come over here. And you also know that if it is a 3D series, it should be 3D and 4s, because the last electron should enter the n minus 1 d orbital, as I discussed with you in the start of the class. So 3d1 4s2 again. Here if it is 22, then 3d2 4s2. Correct? Going further, if it is 23, 3d3 4s2. You just need to swap it. 23, so 32, like that way. Okay. Further, 24, so it should be 3d4 4s2, but this is an exception. Why 3d5 and 4s1? See, because 3d5 is more stable. It is a half filled orbital, right? It is a half filled orbital. 3d5 is an half filled orbital. So if it would be 3d4 4s2, and the other side it is 3d5 4s1, which is more stable. Of course 3d5 4s1, because it is half filled configuration. So the configuration of chromium mark this. It is 3d5 4s1. Don't make mistake over here. Mainly the questions are asked from 3D series, so I'm focusing more over here on 3D series. Now same thing, if it is manganese 25, 3d5 4s2. If it is iron 26, 3d6 4s2. 27, 3d7 4s2. 28, swap it. 82, 8 here, 2 here. 29, it should be 9, 2. Again, 9, 2. Which is better, 3d9 4s2 or 3d10 4s1? 3d10 4s1. Why? Because it is a full filled configuration. So mark over here, chromium and copper are both exceptions. Chromium just because of half filled configuration, and copper just because of fully filled configuration. And then zinc, you'll know the configuration of zinc. Okay, it is a fully filled. So 3d10 4s2. So this is how you will learn the configuration. Now, how to write this down? See, it's very difficult to write it like SCTIV, CR, MN, FE, CO, NI, CU, Z, zinc, ZN. So I'm making you write one trick over here. Okay, so take out your pencils in your textbook, write it down. Science teacher very cruel, मांगे फेर कॉपी, नहीं complete जरा. I'm repeating once again. Science teacher very cruel, मांगे फेर कॉपी, नहीं complete जरा. This you need to remember. This is important. This you need to remember. Okay? Because if you don't remember this, you won't be able to write this. If the question will be asked, tell me the atomic number of nickel. Okay? So how will you remember it is 28? First, you need to remember the way which I told you and write the elements in that way.
Sir, can you please repeat?
Yeah, please. Yeah.
Yes, yes.
Just write it down once again. Science teacher, science teacher very cruel, मांगे फेयर कॉपी, FAIR फेयर, कॉपी COPY कॉपी, NI इज नहीं, कंप्लीट जरा. And again, the electronic configuration, you need to make sure chromium and copper. And now let's talk about the first ionization enthalpy. Now you can see over here the ionization enthalpy of zinc is higher. Why? Because it is very difficult to remove an electron from the valence shell 4s2. Why? Because it is fully filled. And if you remove an electron, you will need to provide more energy. Why an element want to go from stable to unstable? It won't go, right? Every element wants to be stable over here. So if you are removing an electron, you will make zinc unstable. So to make any element unstable, you will need to provide more energy. Okay. So here zinc on the higher side and on the lower side would be scandium. Why? Just see the electronic configuration. See, all the concepts are mainly linked with the electronic configuration. I told about melting and boiling point. That too also electronic configuration, because over there you have to see the unpaired electrons. Then enthalpy of atomization also same thing. Okay, and here also ionization enthalpy. Now why it is lower? See, it's 3d1 4s2. So the electron will be removed from 3d1 and then it will attain a stable configuration, right? So that's why it's a lower. It's on the lower side. Now, do you also want to remember the 4D and the 5D series? I'm making you write a trick for this. Y, ZR, NB, MO, TC, RU, RH, PD, AG, CD. Like the same way I've written, made you write for this. Science teacher very cruel, मांगे fair copy, नहीं complete जरा. Now write it for the 4D series. That is also important. They may ask you, what is the atomic number of RH? So if they ask you the atomic number of RH, it will be very difficult for you to write it down. So first what you will do, you will write all the elements as I say using a trick, and then it will be from 39 to 48. Okay, so from 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. Like that way you will write it down and then you will figure it out. Okay, RH is this one. Okay, so यारी जरा निभा मौत तक रुकावट रह पड़े आग में कूद जा. I'm repeating once again. Y means yari. Yari means friendship. Yari. ZR is zara. NB is nibha. MO is moth. TC is tak. Till you die, maintain the friendship. Okay. रुकावट रह पड़े आग में कूद जा. This is for the 4D series, and further 5D series. Again, they might ask you what is the atomic number of gold. So it is very difficult to remember that way. You will first list down the elements. So I'm making you write the trick for this 5D series. ला हफ्ता ला हफ्ता वरना रे ला हफ्ता. See, you can see la la half hf ta. Varna means w. Ray ओसामा इराक की तरह is just to complete the sentence. Okay, इराक is ir. की तरह पिटाई और होगी. I'm repeating once again. See, write it down once again. ला हफ्ता वरना रे ओसामा इराक की तरह, राइट इट समवेयर इन द मिडल, की तरह पिटाई और होगी. So that way, and also write it the atomic number. Lanthanum is 57. Further, Here it's from 72 to 80. 72, 73, 74, 75, 76, 77, 78, 79, 80. Okay, so with that way you can actually figure it out what is the atomic number for, let's say, molybdenum. Or if the question is asked that what is the atomic number of W, which is tungsten. So with that way you will just list it down, and you just need to remember one thing. 3D series is from 21 to 30, 4D series is from 39 to 48, and your 5D series lanthanum is 57, and further it's from 72 to 80. By example 8.2, why do the transition elements exhibit higher enthalpies of atomization? Again, the same question, the same reason for the melting point and the boiling point. Because of large number of unpaired electrons in their atoms, they have stronger atomic interaction, or you can say they have stronger bonding between atoms, resulting in higher enthalpies of atomization. Further moving on, oxidation states. Again, first thing what you have to do is write down all these elements, 3D series elements, with the way which I taught you. Okay, so write it down. Science teacher very cruel, मांगे fair copy नहीं complete जरा. Like that way, write all the elements. Then I will make you write the oxidation state of all of them. See again, oxidation state is also the same thing which you will remember when you write the electronic configuration of all these elements. So again, scandium is 21, so 3D1 4s2. Same way it will proceed. The exception is chromium and copper. Okay. Now you all know the fact that each and every element will lose electron, and once it loses electron, it has to attain a stable electronic configuration. So these electronic configurations which you can see over here are mainly when any element in its ground state will lose electron to become stable, or basically become stable means has a stable electronic configuration. So again, electronic configuration is still over here. Okay, so what was the configuration of scandium? 3d1 4s2. So if plus 3 means it has lost all the 3 electrons, and it has attained noble gas configuration, the nearest noble gas configuration. 3d1 4s2, all the 3 electrons gone, noble gas configuration reached. So scandium only one oxidation state which is plus 3. Okay, coming to titanium. What is the configuration of titanium? 3d2 4s2. Okay, 3d2 4s2. So once it loses 2 electron, it will become plus 2. And what is the configuration it will achieve? 3d2. Again, unpaired electrons. So that is also stable. In case of d orbital, 2 unpaired electrons. Again, plus 3 can also be achieved. And why plus 4? It will lose all the 4 electrons and become nearest noble gas configuration. So titanium plus 2 plus 3 plus 4. Vanadium again 3d3 4s2. Okay, 3d3 4s2. So starting with plus 2, It will become 3d3. Then again start losing one electron. So 3d3 with plus 2, 3d2 with plus 3, 3d1 with plus 4, and with plus 5, all the 5 electrons gone. Means achieved the nearest noble gas configuration, which is the stable configuration. So that way you need to remember. See, everything you should remember with logics. There should be some logical reason for all these things. The oxidation states which I'm seeing. So everything is linked with the electronic configuration over here. Same for chromium, same for manganese, iron, copper, nickel, cobalt, zinc. Zinc again I told you 3d10 4s2. So it will lose 2 electron, will become 3d10, which is completely filled. So it will show only one electronic configuration, which is plus 2. Copper will show plus 1 and plus 2. Now mark which are important over here that are asked in exams. Scandium is important. So mark it. Scandium is important. Sc plus 3. Zinc is important, plus 2. Copper is very important. Copper shows two oxidation state, which is plus 1 and plus 2. The question is asked. Iron, Fe is very important. Manganese is important because manganese has plus 7 also. Only single element which has plus 7 oxidation state. Manganese. Very popular. Chromium is important. So which all elements I say? One is scandium, chromium, manganese, iron, copper, and zinc. So make sure you remember this. So if I give you one compound, let's say MoO3, can you find the electronic configuration of MO over here? Molybdenum. So basically oxygen. What is the oxidation state of oxygen? It's minus 2, right? So minus 2 is for one oxygen atom. And it has how many oxygen atoms are there? 3. So 3 multiplied by minus 2, which is minus 6. Now all in all, this compound is neutral. So molybdenum should have plus 6. Because plus 6 minus 6 will become 0, and overall the oxidation state of full compound is 0. So that way, using balancing, you need to figure it out what is the oxidation state of a metal in a particular compound. So it's written also over here, molybdenum 6, and also same for tungsten, WO3, it's also plus 6. Moving further, trends in the M2 plus M standard electron potential. So now what we are doing, from M2 plus to M, we need to provide electrons, 2 electrons. Okay, so that process is known as oxidation or reduction. In case of oxidation, there is loss of electrons, and in case of reduction, there is gain of electrons. So, will this metal going from 2 plus oxidation state to 0 oxidation state undergo oxidation or reduction? It has to accept 2 electrons, so it will undergo reduction. So here we are discussing about reduction electrode potential. And you need to mark an exception over here. Copper is an exception which has positive electrode potential. Mark this thing. inability to liberate H2 from acids, which is important. Mark this as important. The general trend towards less negative electrode values across the series is related to the general increase in the sum of the first and the second ionization enthalpy. Okay, so this is basically the ionization enthalpy only. Why? Because see, if you are talking from M2 plus to M, let's talk about M to M2 plus, the opposite of it. That is basically ionization enthalpy only, M to M2 plus. So if any element has high ionization enthalpy, which means it has less negative electrode potential, because both of them are opposite. Ionization enthalpy means loss of electron and reduction means gain of electrons. Okay, so with increase in ionization enthalpy, the values of electrode potential is less negative. Remember this thing. And this value for manganese, nickel, and zinc. This question is asked in exam. Which element has high reduction potential? So you need to mention manganese, nickel, and zinc. Same is for M3 plus to M2 plus standard electron potential. Now you need to provide one electron. Means an element is in plus 3 oxidation state, it will accept one electron to become plus 2 oxidation state. So same thing. See, here also electronic configuration will be taken into account. If an element wants to go from M3 plus to M2 plus, means in M2 plus the electronic configuration of an element should be a stable electronic configuration. If it is stable electronic configuration, then and then only that element will have high electrode potential. I hope you would have learned that chapter electrochemistry. There you can see a table of the, I mean the series of the electrochemical elements. So that same thing is over here. Now coming to the trends in stability of higher oxidation states. Very important. Now when these metals they combine with halides. What are halides? Fluorine, chlorine, bromine, and iodine. Okay, so when these elements, D block elements, they combine with halides, what is the chemical formula of all of them? Is mentioned over here. Okay, so what is the oxidation state of halides? It's minus one, right? Fluorine is minus one, bromine is also minus one, chlorine is minus one. And what we learned the oxidation state of all the metals? For titanium, it was plus 2, plus 3, and plus 4, right? For titanium, it was plus 2, plus 3, plus 4. So if it is plus 2, titanium is plus 2, X, which is an halide, is minus 1. So what would be the chemical formula? TiX2. You know this method, cross method? Ti, you just write plus 2 below, X, you write minus 1 and do the cross. Means Ti1, X2 to form the element, to form the chemical formula of the compound which is formed here. Just write the electronic configuration Ti plus 2, X minus 1, do cross. So Ti1, X2. Same, Ti also occurs in plus 3 oxidation state. So it would be TiX3 as well and TiX4 as well. Okay. Same for vanadium, it occurs in plus 2, plus 3, plus 4, and plus 5 oxidation state. One thing you need to remember, see one thing which is very important. We in plus 5 oxidation state will only combine with fluorine. Remember this thing. If I'm saying X means fluorine, chlorine, bromine, and iodine, all four. But if I'm saying F, which means only and only fluorine, remember this, very important. VF5, underline this, mark it. What I wanted to say is higher oxidation states are actually stabilized by only and only fluorine. Why only fluorine? Because fluorine is very much electronegative in nature as compared to other halides. Okay, so remember this, higher oxidation state means here vanadium the oxidation state is plus 5. So that will be stabilized by only and only fluorine over here. Same for chromium. We had written over there what are the oxidation states of chromium: plus 2, plus 3, plus 4, plus 5, plus 6. Okay, so you can see plus 2, plus 3, plus 4, plus 5, plus 6. Now again same thing, the higher oxidation state which is plus 5 and plus 6 are stabilized by fluorine. Okay, mark this as important, underline this as well. Same for manganese. Now you might be thinking that sir, manganese plus 6 is also there, but plus 7 is also there, but why is it not over here? Because those elements are actually not found in nature. MnF6, yeah, or you can say Mn plus 7, or MnF7, sorry, MnF6 and MnF7 are actually not found in nature. They are not discovered yet. So Mn is only restricted to MnX2, MnF3, and MnF4. Same for iron. FeX2 and FeX3. If it is FeX2, the oxidation state of Fe is plus 2 and plus 3. Also Fe has plus 4 and plus 6. But the halides, the formation of halides with these metals is not possible, is not found in nature with iron having plus 4 and plus 6 oxidation state. So the important one here are mainly chromium, manganese, iron, copper. Copper is very important element. Okay, and zinc. Same, zinc has plus 2, so Z and X2 will be there. Copper has plus 1 and plus 2, so CuX and CuX2. Nickel has plus 2, so NiX2. Very easy to remember. Now, here also there is an exception. All copper plus 2 halides are known except the iodide. Means, here you can see CuX2 over here. CuX2, but there is an exception that X cannot be iodine. It can't be Cui2 because Cui2 never exists in nature. What exists in nature? Cu2i2, this one. Okay, so here there is an exception which can be asked in your exams, very important thing. Cu2i2 exists in nature and not Cui2. Remember this. Again, this table is also important. These are mainly for the oxides. Now you should remember what is the oxidation state of oxygen? 2 minus, right? And for scandium, what was it? Plus 3. Only one oxidation state. You can see scandium plus 3 oxidation state. Also on the table at the back. Scandium plus 3 oxidation state. So how I'm going to write the formula? Scandium I'm going to write plus 3 and oxygen I'm going to write minus 2. Now I'm doing the cross. So Sc2O3. That way you need to make a chemical formula here. First write the oxidation state of both the elements, scandium plus 3, oxygen minus 2. Do the cross, scandium plus 2, oxygen, sorry, Sc2O3. Same for titanium, it shows plus 2, plus 3, plus 4. So why TiO? Because oxygen is minus 2, Ti is plus 2. Okay, so it should be Ti2O2, right? But that 2 is taken away. We have written over here the empirical formula, not the molecular formula. I hope you know what is the difference between empirical and molecular one. We have taken the ratio. 2 is to 2 means 1 is to 1. So TiO that way. Same for TiO2. Here Ti has plus 4 oxidation state, and Ti2O3 means Ti has plus 3 oxidation state. Same for all the other elements. And which are the most important elements which you will learn further? Mn2O7, MnO2, CrO3, Cr2O3, even Fe2O3, Fe3O4, FeO. This you learned in metallurgy chapter. These are the ores of iron: Fe2O3, Fe3O4, FeO. So here the important ones are same: candium, titanium, chromium, iron is very important, copper and zinc. Mark this all as important. Further we will do in the next class. I hope everyone would have marked the important things in your textbook, the important notes. Okay, thank you so much. You can leave. Thank you.